45 degrees line where both are equal. So this is called equal error rate. So for this particular algorithm, this is my equal error rate. This point, this is the equal error rate. This value will, let's say 0. Let's say 19 or something. So here my EER, equal error rate, is equal to 19. So in this way, I can quantify my matrix, that how good or bad is my algorithm. Okay. So just a kind of an extra thing I want to tell here. Equal error rate may not be the best metric all the time, because you may require a very small false alarm rate. So then you will not be keeping your threshold somewhere here. You will keep your threshold. If you want to keep let's say this is the false alarm rate. If you want to keep your false alarm rate very small, then you will be operating somewhere here. So that false alarm rate can be low, even if miss rate is little high. You may not operate at EER, but at some other point. Okay. So with this, we have come to an end to the basic concepts required in audio event detection. Now I'm going to start the next topic, which is little advanced in the sense that this problem is of data imbalance. But before I move to that, I would like to ask if there are any questions. Are there any questions at this point?
So I want to ask one.
Somehow I'm not able to hear.
So whether I'm not audible to you? Hello? You can't hear us? Okay.
Oh, I'm sorry. There was some problem with the microphone. Now I can hear you. You can also hear me, hopefully.
Yes, sir. So can you hear me?
Yes, please.
Sir, yeah, we got one question. Sir, Dr. Hari Murugan is asking about, can you elaborate on EER of 19? What does the 19 indicates?
Okay. Let me go back to my slides. Okay, so this is my false acceptance rate. This is my miss rate. I don't remember exactly which axis was FAR, but just assume this is the one. And I can tune my threshold to any of these values, right? If I make my threshold very large, which means my threshold is very stingy, it does not accept even a high YIL as the detection. So it will accept a detection only when my YIL is more than 0.9, which means my network has to say my probability, the probability of this event being the clapping sound is more than 0.9. Then only my threshold will allow it, and it will say, okay, I will raise an alarm now. Okay, that yes, clapping is detected. And then you can compare that alarm with the output to see whether it is correct or not. So so here you have very small false alarm rate, because false alarm will not be so high. Right? There will be some, but it's comparatively low. Similarly, here when you are here, then your miss rate is very small, because you are accepting everything. Your threshold is so weak, it allows every sound and keeps raising the alarm, or keeps raising the flag that yes, it's a clapping, yes, it's a clapping, yes, it's a clapping. And therefore it's very less probable that you actually miss any clapping sound. So your false alarm rate is very high and miss rate is very low. But both these regions are not very desirable. What is desirable is something in the middle, where you can actually have a not too high miss rate and not too high false alarm rate, somewhere in the middle. And this is one such point where miss rate and false alarm rate are exactly the same. So miss rate and false alarm rate are exactly same for some value of theta, right? And at that value, whatever is FAR and whatever is MAR, you call it as that value as EER, equal error rate. So this is a metric, or it quantifies how good is your network. Because if your network is good, then equal error rate will be small. Let's say you're comparing two different networks, let's say the black one and the red one. These are the DET curves of both these networks. And if my black network is better, then it will have a smaller EER as compared to the red one. So when I say EER of 19, it means there is some threshold value for which false alarm rate is equal to miss rate, and both of them are equal to 90. So in geometrically, you want to see that if this is my DET curve, and if I draw a line which is at 45 degrees, then it intersects this curve at this point, 19. So the closer this point is to the origin, the smaller is the EER and the better is the method. Yeah.
So one more from Vishnu Thakur. So it is about getting a good trade-off between precision and recall.
Yeah, exactly. So false accept rate and miss rate are kind of complementary to precision and recall.
Anyone else? So, sir, I want to ask you something that if, yeah, we have one more from Pyali Datta. How we can evolve MFCC feature here?
So MFCC features evolve. What is the meaning of evolve here?
Pyali, please.
What is the meaning of evolve here?
So, Pyali, can you elaborate your question? Evolve means?
I think she means involve.
Sir, it's like how we can use the MFCC feature to make this model.
Okay, good question. Let me go back to my presentation. Yeah. So the input to the model could be MFCC features, right? This input where we design. I have used LFB features. Instead of LFB, you can use MFCCs, right?
So what is the advantage of MFCC, and what is the means? Is there any advantage to use the MFCC?
Okay, good question. So MFCCs, they measure the spectral envelope, and they take the spectrum. To estimate the envelope, they perform a discrete cosine transform of the magnitude spectrum in the log domain. So basically, which kind of finds a representation for your spectral envelope. And LFB features are doing something similar. They are also trying to estimate the spectral envelope, but their method is different. They take the bins, filter bank energies, the bins, and they average out the energy in that each bin. And that's how they quantify the envelope. So both are trying to capture something similar, but their calculation techniques are different. Therefore, their performances are also different. Yeah.
So, as you have depicted that if someone claps, then that model uh, predicts or retrieves the frame or the duration of that clap. Sir, what if the amplitude is very low for that clap, and we have overlaps of different audio signals. So how that is being handled?
Yeah, so that becomes difficult to detect. But then, if you have trained your model on such kind of samples and your model is able to detect it, so it can detect.
Yes. So can we impose some kind of filters while testing for such audio signals?
Filters means?
uh, in order to enhance that those amplitudes. I mean, the kind of we want to, as we remove noises from the signals. So are there something that we can retrieve that particular, which is very faint kind of signal, but it is significant for the it is significant for the user or the one who is checking the signal, but that is very faint, amplitude is uh, very less. I mean,
Yeah.
the signal is
I got your more emphasis on such peculiarities of your signal, but but today the trend is that let us design the machine learning systems or the neural networks themselves in such a way, or train them in such a way that those peculiarities are captured by the network directly. Because the reason is, if you design a signal processing technique, it is not optimizable, right? It is just a static technique which you use your intelligence and you make something. But this technique, neural networks, they are optimizable and they learn from the data, and looking at the large data, and if you train them properly, they can learn what are those peculiarities statistically. So they sometimes, or most of the times, they are more effective rather than doing some pre-filtering or pre-enhancement of the signal.
yes, sir. Thank you. Sir, as you
So,
yes, Gary, please.
so somehow we can solve the problem of overlapping, situation overlapping, means with the time interval, means if we consider the time interval, then somehow we can solve that overlapping problem with using the time interval.
Yeah. So in the segment level classification or segment level labeling, you kind of fix your time interval. I want only audio segments of length 10 seconds, audio segments of length 5 seconds. And then you're mapping this entire segment to those labels. So, but as you are saying that if we have time intervals, then which means you are saying that we do frame-wise analysis, that you have small frames which are very short in length, let's say 25 milliseconds length. It is very short. If you do frame level analysis, certainly can uh, you can you can do more finer analysis in time, but the overlapping will still be there. Let's say if in the 25 milliseconds frame, there are both the sounds present, speech as well as traffic noise, both are present, then they are present in the same frame also. So you still have to do similar analysis to be able to separate them or to detect them. But, yeah.
Sir, as you have depicted that birds' voices, or what do we call bird cherubs, different kind of cherubs are being deployed for uh, knowing about them. So, what are the challenges, or are the people are doing that as in ancient times? Birds gives us the information of any kind of disaster, or like certain caution for the danger. So, what are the challenges and involved in this? If
I,
we compute uh, cherubs for this purpose.
Yeah, certainly this can be done, but I don't know any work somebody is doing in this direction yet. But certainly, if if you're an expert in that area, means you know what the sounds mean, then you can make a classifier to automatically detect those classes.
Yes, sir. But for this, I'm sure we need, first of all, we need I mean, the way they check it when um, they find that something is gonna happen which is not correct, or something is some they want to depict some danger sign. So I think we don't have data set for that.
Yeah, you have to make your own data set. But even to make the data set, you need some expert who knows how to do it.
Yes, yes,
Some domain expert who knows what do these chirps mean.
yes, definitely. Thank you, sir.
Yeah.
I think no more questions, so you can continue.
Thank you. So currently, whatever we saw, the models, they were something like this. You have some input features, you have some output classes or output labels, and then you have a classifier or a machine. To train this machine, you are using training data. Remember, if you remember this slide, I explained that this PI are the actual labels for my input, YIs are the estimations by the network, and if you know for a particular X, what is the target T or the ground truth T, then you can use this loss function and you can optimize your network and find the optimal weights which can give the right output for your input, right? So essentially for this, what you need labeled training data, which means labeled means you have X and you have the corresponding T, the target labels. Using that, you can train your network. So this is how it happens. You have training data. Let's say there are three classes: blue, green, and red. It could be three sounds, maybe clapping and speech and music. Let's say you want to classify your audio into in these labels. Your training data is like this. This is called a balanced training data. Why balanced? Because all three classes have same number of or similar number of samples. Let's say there are 100 audio files for speech, 100 audio files for clapping, 100 audio files for music. It's a balanced data. But what happens if my data is imbalanced? Which means I have got 1,000 files of speech, 100 files of clapping, maybe 50 files of music. So it's like you have so much data for a certain class, so little data for certain other class. This is called imbalance. There is no balance in the data. So this is called imbalanced data. Now the question is, how do I train my classifier on my neural network to train my network from this imbalanced data? And it generally means that the classes which have got very small data, they will be overshadowed mostly. Because if my classifier does very well on just this data, then these classes anyways are very small. So in the loss function, their contribution is so small, so they will be ignored. My optimizer will, let's say, my optimizer gives a result that everything is red class. So what does that mean? My loss function will have contributions from these samples and these samples, whereas these samples will say, basically they will say zero error. Only these will give high error, right? But even if they combine together, how much contribution can they make? So these class will kind of eat away the other classes. So this problem becomes very severe in real life. It's called imbalanced data. Now, a common solution is used. Okay, you have a problem with the weight of that class. Just enhance the weight of the class. So here what I have done is, I have multiplied a WL, this term. I have multiplied this term with the contribution of a particular class in the loss function. And this term is inversely proportional to the size of the class in the training set. let's say my clapping had only 100 samples, then this WL will be, let's say, 1 upon 100. And my speech has 1,000 samples, so my speech will be 1 upon 1,000, which means the contribution of speech is shrunken, and the contribution of clapping is relatively more. So which means that ultimately, if you look at the entire data set, they have both equal contribution, right? So speech has got more samples but less weight, and clapping has got less samples, but each sample carries more weight, so that overall the weight is balanced. This is the common solution to handle data imbalance problem. Now, the solution which I proposed here in this work is this. This solution is inspired from the geometry, that how this is my imbalance data. I distribute, or I divide, or I further split my big class into smaller classes. So much so that each cluster is almost similar in size. Right? Let's say there are 100 clapping sounds, 100 music sounds, and let's say 400 speech sounds. Then I will distribute into four clusters, so that each cluster has got 100 samples. Right? And if, let's say, my speech had 1,000 samples, I would divide it into 10 heaps or 10 clusters, so that now I will have 2 plus 10, 12 clusters. So, okay, so this was the first thing, that I will divide my data, and so that I can do better training. Now, let's look at this architecture of the network. Here, I am mapping my input to the output, not directly, but in between, I have something called embedding. What is an embedding? Embedding is a vector of fixed length. Let's say it is an output of a neural network, then it's a vector of fixed length. It may not have any meaningful, interpretable, interpretable meaning, but these vectors, they represent the input. So if I'm mapping my entire input, the whole matrix, into one embedding, and this embedding will be different for different audio files, right? Now I can train my network to make a structure in the embedding. Let's say I want to do classification, so I will make sure that these embeddings are clustered together for different classes. These are class-wise clusters. So basically, I can do many interesting things with the geometry of these embeddings, and that's why these embeddings have become a very popular concept in machine learning. If you have heard of some recent developments, let's say in BERT model, or wave to vec, or word to vec, these are very popular models which basically map your input to a mapping or to an embedding, and this embedding represents your input, and this embedding contains all the useful information which you want to extract from your input. So now in our case, this is the geometric intuition, that let's say this is my entire space of embeddings, which means, let's say each embedding is a vector of fixed length, right? So this is the entire Euclidean space of that dimension. Let's say it's Euclidean. So, okay, but in our case, we didn't consider it Euclidean, we considered it as a spherical or hyperspherical space, which means that the embedding vector is normalized to have unit L2 norm. So, which means it lies on a sphere or hypersphere. Now, this is how my space looks like. Now I want to induce a structure in the space, and the structure is something like this. I want to make clusters so that each cluster represents a pure class. If this cluster is speech, then it should be speech. This cluster is music, it should be music. This is clapping, this should be clapping, right? And they should not mix into each other. They should stay separately, right? So this is what is the significance of embedding, that I make it in such a way that I can cluster things together. Now, the geometric intuition, how do I handle imbalanced data with the help of these embeddings? So this is the technique. And I have got, let's say, some distance metric in this embedding space, let's say cosine similarity metric. I want to, let's say I have a point xi and it maps to this particular point. In the embedding space, my xi maps to this particular point. Now, I want to bring it into a cluster. Let's say this is a speech class. I will train my network in such a way that this embedding moves closer and moves far apart from this cluster and moves very, very far apart from this cluster of another class. So I design my loss function in such a way that my loss will be small if this embedding of xi, let's say this xi is actually clapping sound, then this is very close to the centroids of one of the clapping cluster, and it is away from the centroids of other clapping clusters, and it is very, very far away from the centroids of other classes, let's say, which could be let's say which could be music. This was speech. Okay, so this is my geometric intuition. Now the question is, can I design a loss function which can do this? So people have used contrastive loss or triplet loss functions, but in this paper we propose some different kind of loss function. So this was this, that you have the embedding, right? This is my embedding, and when I want to map my embedding into the cluster, my embedding vector, I multiply it with the weight vector, right? That is what we do to map it into a cluster. And this weight vector and this embedding vector, you do a dot product between the two, and then you get HI. Now the philosophy is that I will design this non-linearity. Here S1 is the cluster S1, this one. So this is the cosine similarity of the embedding with the centroid of this cluster. So you see this term is designed in such a way that if my K1 is my actual cluster, my desired cluster, which is speech in this case, then S1 should be large, it should be 1, close to 1, and S2 should be small, S3 should be small, so that overall this term becomes maximum, right? If this xi, this embedding of xi comes very close to this point, then S1 will become very large, right? S1 is a similarity. It's the inverse of the distance, you can say. The similarity is very large. This is very large. This is very small. This is very small. So the overall term becomes closer to pi. And so, and if this does not satisfy, then my overall term becomes close to 0. So I can use this to define my loss function. So my loss function is minus log of this term. So y negative small when my goal is achieved. When the embedding moves closer to the centroid, my loss should be minimum. That's why negative sign is there. And y log, log is just to make it, this is an exponential term to make it small I with a log term. Now, when we try this, when we implement this into our machine and we train our machine to minimize this particular loss function, then I tried this on a toy data set so that I can visualize it. Toy data means very small dimensional data. My embedding is 3-dimensional. You can see it's a sphere. The space lies on all the embeddings, they lie on the sphere of unit radius. And in the beginning, before the training started, everything was mixed together. There are no clusters here, right? But when the training is proceeding, you see some structure is evolving, some things are getting segregated. And as training proceeds further, you see clearly the clusters emerge out. Right? So this, when I minimize this loss function, automatically these clusters emerge out. You can see the blue class, the green class, and the red class, which had got 4 times the samples. You can see there are 4 heaps in it. And if you see from this same figure, you see from another perspective, it looks like this. You see this class, and this class, they are completely separated. So this means our network has learned the embeddings very nicely. Now the question is, how do we do classification finally? I'm going to shove it 520. So how do we do the classification? You introduce another layer which will predict the final class, which basically combines everything and gives the final class. So I add another layer, dense layer. I train the last layer by freezing the previous layers, and then I unfreeze the previous layers. Also, I do an end-to-end fine tuning, and that makes my classifier. Now we tested the results over some standard data sets. Audio set is a standard data set available from YouTube videos made by Google, and so this was my data set. You can see large variation. Dog barking sounds are 13,000, baby cries are very less, just 2,000, gunshots are 4,000, and background audio means everything, speech or etc. That is 36,000 samples. So a lot of imbalance here, but we made it even more severe for our testing purpose. Okay, these are the models we use. We use LSTM models with this configuration, CNN models with this configuration, and then we trained with the very standard things. But important thing is, okay, we used 8 parallel GPUs. It was a huge setup. Okay, then LSTM model with the 6:1:2:16 data ratio, which means this class is 16 times, this class is only 1 time. Means that their sizes are of this ratio. And the results which we obtained with LSTM model are something like this. So you can see the blue one is the baseline. Baseline is simple weighting. If I simply weight my loss function based on the class size. But the proposed methods are, they use the embeddings, and you can see there is an improvement. So with the embeddings, the results improve so much, right? Your equal error rate improves so much. How in the baseline equal error rate was 21, and here it has reduced to 18.3. Right? It's quite a lot of reduction. Similarly, when I change my model to a CNN model with the same training scheme, I see my results have improved. If you compare LSTM versus CNN, CNN is doing better. CNN has better performance. But even if you compare across the 3 training schemes, you see the proposed method gives much better results, much smaller error rate, equal error rate. Right? So this is what the results were. Now, yeah, and further, actually, I thought I will also share with you some hands-on example. So this hands-on example, maybe I will ask you if you have time for that. I made, there is a Vipul notebook on which I made an example. If you wish, I can go through it. With a simple 10 class classification. There are 10 audio labels, and for each file, there are multiple events present there with an onset and offset time are given. And you want to predict the same thing, segment level labels. So, but I stop here for any questions, and if you think we should proceed, then I can show the Jupyter notebook also. Yeah. Any questions, please?
Any questions? So I think you should proceed.
Okay, let me open my Jupyter notebook then.
Yes, sir. Sir, I have a question.
Please.
Sir, sir, can we do behavior analysis with your model? Like
Which analysis?
behavior analysis.
Behavior analysis.
Yes, sir. Sir, like I was thinking that if a person is angry, the number of words he speaks is larger and the pitch is also higher, and the word he uses is also a certain kind of word. And when a person is in normal situations, the number of word is less.
Yeah. So you are defining some man-made or an expert-made rules that, okay, number of words, count the number of words, and based on that you make your classifier.
Yes, sir.
So this is a possible way. But if you want to use machine learning, then machines can also learn many things, right? They can directly look at the audio of your subject and then classify whether it's angry or not. And then the machine can learn from your training data how to make this mapping.
यस सर. सर जैसे कि एक मेरे पास एग्जांपल भी था. मेरे घर के पास ना एक फैमिली ऑफ क्रो रहती थी मेरे घर के पास. तो जब वो नॉर्मल मतलब नॉर्मल टाइम्स में उनका जो जो मतलब जो साउंड क्रिएट करती थी वो बहुत लेस होती थी. पर जैसे कि कभी स्टॉर्म या कुछ वाइल्ड फायर होती थी तो उनकी जो नंबर ऑफ जो उनकी साउंड होती थी वो इंक्रीज कर जाती थी. तो हम इसका यूज़ भी कर सकते हैं मतलब कि डिटेक्ट करने में कि जैसे कि कोई स्टॉर्म है या कोई फायर है, वाइल्ड फायर है, तो ऐसा कुछ भी.
If you can record such audio and you can make a classifier to detect if that kind of audio happens again.
यस सर.
Right. Any other question? Yeah. So this is the sample notebook. So you can,
Sorry to interrupt you, sir. Sir, we can record this session, right?
yeah, sure.
Yeah, and we are think to upload in Spotify and YouTube also.
Okay.
With your permission, sir.
No problem.
Thank you, sir. Thank you.
So this is a Jupyter notebook. I think there is not much time left, only 2 minutes left for me.
So we can extend, sir. No problem with time. I hope for you. If you are fixed.
Sure. So I will just quickly go over it. The concepts which I explained in theory, now you can see them here in practice. So you have some database. So if I want to show you the data set, share my entire screen. Okay. So let's say you have an audio. Let's say this one.
Up and down.
So you see, this was the file, and there was an onset of alarm bell ringing, again alarm bell ringing, again alarm bell ringing, and then there was some speech. So there are precise times in seconds given here, onset time, offset time for each event, and then there are labels given. What are those events? This is how the data looks like. This is from DK's challenge, and you listen to the audio, you saw so this audio is my input, and these are my outputs. Okay, I'm not predicting the onset and offset times for a particular file. I only want to predict whether these events are present or not. And these are all the events which are listed here. Okay, so now the question is, how do we make our model? So let's come to the Jupyter notebook here. So we have got the data set, and the labels are available in a CSV file, comma separated values file in this format. So I read the CSV file, and I read the So basically, I read the audio files here using Librosa library. It's a library available in Python, which loads your audio files, and it trims the audio to 10 seconds. There's some pre-processing, very simple formatting stuff. So I will skip this part. Then you can visualize your samples. This is my audio file. And these are the labels which are available, the same alarm, speech. And you can listen to the audio which I already played. Okay, here we are doing some more sampling, making it even smaller samples. Instead of 10-second samples, now we are making 0.5 seconds audio segments. And yeah, and finally, this is the distribution, class-wise distribution. You can see it is almost balanced, but okay, some differences are there. Okay. Then we use MFCC features. We extract the MFCC features using librosa library from each segment, and then we create what is context here. Basically, it means the list of the entire data set. That's the context, nothing very special. Then training and validation. So we split our data into training data and validation data. Why do we need validation data? If you remember, we set some threshold values, right? Or some hyperparameters which we want to tune in our network. So for that, we use some validation set, like to set my threshold values, etc. So I use some data, which is called validation data, which is same as training data, but just that I don't use it for training my network, but I use it later for fine-tuning my thresholds or hyperparameters. Now I come to training. So for this machine learning neural networks, we use Keras library. It is a part of TensorFlow library, which is very popular. I hope you have heard about it. And I can add my LSTM layers, then dense layer. Like you see, there is a single LSTM layer with 128 LSTM units, and followed by a dense layer which has got only 10 neurons. Because there are 10 classes in the output, there are 10 neurons. So this model is the basic model. There is no weighting, there is no embedding, nothing. Very simple basic model I'm presenting here. For your user, I'm here it is RMS crop optimizer is used. Loss function, very important. So we are using binary cross entropy loss. I discussed it in the theory. And the matrix which I'm using here is accuracy. But these metrics are only displayed during my training. You can see here when the training actually happens using fit function. When I actually do the training for 50 epochs, 50 epochs means the entire data is used 50 times turn by turn. So this is what I get in the first epoch. My loss was very large, accuracy was very small. But as my training is proceeding, epoch after epoch, you see my loss is decreasing, and my loss becomes smaller and smaller. It goes down to 0.0968. You can make it even further smaller, or you can do different things to make it better, but okay, I'm just showing that how it is decreasing here. And, my model is very simple model, just single LSTM layer and then a dense layer. Then I use evaluation function to evaluate my model, right? And then, okay, now I want to do some more kind of evaluation. Let's say I want to see the confusion matrix. Then I can use some libraries like sklearn, etc. You can also write this confusion matrix function on your own. It's a very simple thing, right? I already discussed with you. Very simple to make. But if you don't want to write on your own, you can use the library also. So this is how the confusion matrix looks like. You can see the true positives are very large in number, but there are some false positives also. And here, true positives are very large in number, but there are some false positives also. So overall, the F1 measure is 0.73. Yeah, you can compute equal error rate also, but somehow in this, we did not compute equal error rate. We computed F1 score, which is the harmonic mean of precision and recall. So, but you can use it. Okay, so that's it. So, thank you very much. If you have any questions.
As I said, Vishru want to ask something. Please, Vishru.
Yes, please.
Vishru, do you want to ask something? Vishru?
Am I audible?
Yes.
Yes.
Yeah. Yes, sir. So this was for the baseline model, right? Or the like you discussed, because you discussed two approaches. Like in one you told about the baseline model, and another one use embedding.
Yes.
Okay, that is what I was asking. Actually, my mic wasn't turning on.
Anyone else want to ask something?
Sir, I have got one question. Sir, the data set you have used, whether it is open source, can be accessed somewhere?
Yes.
Like that Craig and Charles.
Yes,
Okay.
it is. No, the crime data was audio set data. It's open source. And the other data set which I used in the Jupyter notebook, that is also open source. It is DK's challenge data. Both are open.
Okay. Okay, sir. Thank you.
Anyone else?
So I'm failing to understand it, sir. This was the example of which model? The LSTM model without embedding, or the baseline model without embedding? Like you compared the models, the EER scores of different models. So this was the example of which model exactly?
Okay. This model was, it used binary cross entropy loss function without weights.
Right.
You can introduce weights also, but this with one simple line you can add weights also. I didn't do that.
Sir, I have seen in your profile that you have also worked for automatic music tutor. So, sir, for Indian classical music, sir, are there any other means to generate other than MIDI if you want to generate the music for classical music?
MIDI does not work for Indian classical music because Indian classical music has continuous notes. There are no discrete notes.
Yes.
That's why, yeah, MIDI is not a good format to store Indian music.
Yeah, so we cannot we cannot add micro tunes to MIDI, so that's what the problem. So how can we generate that for classical music?
What do you want to do? You want to generate or you want to store?
Sir, I want to generate.
For generation, then you generate continuous frequency values. So MIDI is storing the frequency values, the notes.
Yes.
For Indian classical music, you will not store the notes, but you will store the continuous frequency values so that you can capture the entire.
You are freezed. I'm sorry, sir, you were freezed.
Okay, so you store the entire frequency values. You store all the frequency values instead of the notes.
Yes, sir. So, okay, so that will be some machine generated music, like, right? It will generate or we can clone with the available sounds as we do for voices.
I didn't get it. We can clone means?
I mean, nowadays as the voices are being cloned and then reproduced, so can we clone certain instrument or some vocals and then can reproduce those as our generated model? I mean, as our generated audio.
Yeah, we can do that. Yes. Yeah.
So, can you suggest me some data sets available other than HRM music data set?
Maybe we can talk offline about it, the details.
Sure, sir. Sure. Thank you. Any other question?
Like, sir, neural style transfer in the image modeling. So, is it possible in sound also, like that, of a certain node, you can transfer the output of the different instrument, like analyzing the nodes with a certain instrument and generating a different audio from another instrument. Is that possible in this?
I didn't get the question. Could you please repeat once?
Like sir, we have a neural style transfer that we do in computer vision. So similar to that,
Which transfer?
neural style transfer.
Neural style transfer. Okay.
Yes, sir. So, sir, that kind of thing, is it possible in sound also that you can generate a certain node in a different instrument, the certain node in a different instrument? Is it possible in it, sir?
I have not worked in it, but should be possible. We can explore that. It means if it is not done, then we can do it. But certainly,
That's what I'm asking, sir. Is something running over it, something, sir?
Okay. I am not aware of such efforts, but it seems doable.
Right, sir.
Because there is something called voice conversion, which is very well done by machine learning.
Yes, sir.
You can convert the voice of one person into another person.
Yes, sir. Yes, sir.
And for style also, it should not be difficult. It should not be impossible. We can make some.
Yes, sir. And the detection of a source of sound, like you gave us the example of gunshots, that in a place that we can detect the sound source of a gunshot. So, sir, in current scenario, is it possible, sir, to detect a certain sound source in a noisy environment?
Okay, so when you say sound source detection, it means you want to localize it in space, right? Where exactly it is. Right?
Yes, sir, to pinpoint a position where it is.
Yeah. So for that, you will require multiple microphones.
But sir, is sounds a translational invariant, sir? So how can you perform a transformation so as to pinpoint detect certain sound in noisy environment, sir? So like you said, that in a certain frame, you'll get both the relevant sound and the noise also. Whatever transformation you make on it. So, sir, how is it possible that you are detecting a source in noisy place, sir?
You can detect the direction from which the sound is coming, right? So let's say you have an array of microphones and sound is coming from this direction, then this array is simultaneously recording the audio, so it can know the phase difference. Let's say the sound hits this microphone first, then this microphone, then this microphone. There will be a phase difference, and using that phase difference, you can detect the direction.
Right, sir, right.
So,
in this example, sir, you used MFCC instead of LBE, but like you. So, what kind of difference can we expect? Like if we use LFBE in this example of LSTM.
So my experience says that LFBE features may improve your performance slightly. I mean, they may improve. LFBE may improve your performance slightly. But yeah, then again, empirically, you have to test.
Okay, sir. Thank you, sir.
Any other questions? Okay, so thank you, sir. Thanks for this great lecture. It was very lively, engaging, and educative. So we are most grateful, sir. Sir, thank you.
Thank you. Thank you, everybody, for patiently listening and asking questions nicely. If you have any further questions, I'm available. You can email me. And yes, if you want to work in music, then we have an active group here, and you are most welcome to see what we're doing. Thank you.
Thank you, sir. Thank you so much.